Hello Year 11s, this is the electromagnetic waves exam. Just make sure you have your green pen and your blue pen in hand. So the first question says, here is an incomplete electromagnetic spectrum and it has all of the 7 different electromagnetic waves, some of them blanked out. You should remember your mnemonic, as I've written on the side. Rich men in love use extra gel, and it should be a way to figure out what they are. So radio waves, rich men; microwaves, infrared; love, use, ultraviolet; extra, gel, gamma rays. So let me add these in, and it should be light, as in visible light, infrared, and finally radio waves. So which is the group positioned in label B? Well, label B here is infrared. Next question, draw a line to each device to the electromagnetic waves. One has been already done for you. Now before I'm drawing the lines, I am firstly thinking about the wavelength, the frequency, and the energy for each of the waves. I always start with radio waves, and this is how I remember. LLL. It has the longest wavelength, as you can see here as I've drawn it. They have the longest wavelength, they have the lowest frequency, and they have the least amount of energy. And therefore on this side they have the shortest wavelength, the highest frequency, and the most energy. And it's really good to get into the habit of being able to draw a wave out, but also knowing those 3 different properties there. So drawing between the two, you will have the radio waves are for radios, of course. The infrared is used for TV and remote controls, and finally in a filament lamp you get visible light. Make sure you know for each of the different EM waves, you know what their different uses are. Okay, next question then. Which electromagnetic wave can be produced by oscillations, so moving up and down, a charge moving up and down in electrical circuits? Well, the answer is radio waves. As a reminder, I've drawn here an object where the charges will oscillate to create the radio waves is called a transmitter, and the one that will absorb the radio waves is the receiver. We have an X-ray image of the human skull. Ta-da! And you have to complete the sentence using the answer from a box. X-rays can be dangerous to people because X-rays are ionizing radiation. Is anyone there that makes sense? Bones show up white on the photographic film, as you can see there, whereas the flesh, so for example the skin or the tissue, is not shown. Why? Well, very simply, bones are absorbed by the X-ray. So actually, in fact, this means that the film is not exposed. Whereas X-rays can pass through flesh and tissue, and that's why they you can see they are completely blacked out, and you can't see they're not white anymore. Next, here we see the total dose of X-rays received by the human body when different parts are X-rays. So we have the head, the chest, and the pelvis, and on the right here we have the dose, and you can see all the dosages are not of the same units. So let's make sure that they're all the same units. Firstly, the SV stands for sieverts. So we have sieverts, and we also have millisieverts. If we are getting smaller, remember we are then multiplying, and in this case we are multiplying by 1,000. If we're getting bigger, change the B to a D, we're dividing, and so therefore we divide by 1,000 there. And let's make sure they're all the same. So if we divide the chest dose by 1,000, 4,000 divided by 1,000 is 4 sieverts, is our standard units, and the head 3 sieverts are our standard units. The next question linked onto that says here to calculate the number of head X-rays that will equal the dose of 1 pelvis X-ray. So we write this out again. The head X-ray, we see 3 sieverts, whereas the pelvis X-ray 60 sieverts. So how many head X-rays do we need to equal the amount of pelvis? Well, very simply, you do 60 divided by 3, and the answer is 20, and it's 20 times. There are no units because it's just the number of times. Which of the following is another use of X-rays? X-rays are ionizing radiation, same as gamma rays. They can be used to kill cancer cells. And I'll add here use of gamma rays as well. The other one you should recognize is in TV remote. This is the use of infrared. And the final question in question 2 is explain why a pregnant woman should not normally have X-rays on the lower body. And a reminder, a woman who is pregnant, it will have most likely after the embryo stage a fetus. So she's probably with a fetus in her uterus. So why not? Well, firstly, X-rays increase the chance. They increase the chance. That's the first mark of DNA mutations. That is a second mark. The final mark says that mutations are usually harmful to a growing fetus. Question 3. Electromagnetic waves have many uses. There are 2 ways of sending information in terms of communication using electromagnetic waves. Now here, let me start on this side. I have drawn an extra layer. This is an electrically charged layer on the Earth's upper atmosphere, and this is known as the ionosphere. And as you can see here, microwaves can pass through the ionosphere, whereas over here on the left I should say, here radio waves, so shortwave radio waves, are reflected by the ionosphere. So here I'm going to add short wave radio waves, and they are reflected by the ionosphere. So which one is sent to and from satellites? Well, it's the one that can pass through the ionosphere, and that are microwaves. The other known example that you need to know the use for microwaves are used in cooking food, of course. Okay, next question. What property makes this suitable for satellite communication? So is what I've mentioned here. Very simply, it can pass through the ionosphere. Here we have a graph next which shows different frequency radio waves can travel different distances before they're reflected. So we can see here low frequency radio waves will hit about 75 kilometers from the Earth's surface and then be reflected. So in each case it's been reflected. Use the information to describe the connection between the frequency, so low, medium and high, and the distance through the atmosphere before it's reflected. Now notice this is just a 1-mark question, so you're most likely not needing to use data because it doesn't ask for it either, and therefore the answer to this question is very simply a higher frequency. The higher the frequency, and you can see here the high frequency, the further the wave travels. Further it travels before essentially it becomes reflected, before reflection. Okay, calculation question now. So electromagnetic waves travel at a speed of, and you should know it, and standard form is 3 times 10 to the power of 8 meters per second. Radio station transmits wave at a wavelength of 20 meters. So this is speed, and remember we use the letter V for speed. 20 meters, we are looking at wavelength. And finally, you are calculating the frequency in kilohertz. Now, this is important that you are looking specifically for kilohertz. Show clearly how you worked out your answer. So, let's add in our values. Firstly, we have the speed, which is 3 times 10 to the power of 8 meters per second. Then we have the wavelength, and here it's 20 meters. And finally, our question mark hertz for the frequency, but we must remember we want kilohertz, so we draw an arrow and write kilohertz. And just a reminder to get from hertz to kilohertz. So again, if I write on the side, you have hertz, you have kilohertz. You're getting bigger, so if we take the B and turn it to a D, other way around, you're getting bigger, yep, and in B to a D, you're dividing by 1,000. In this case, you are multiplying by 1,000. So in this case, we want to divide by 1,000 our final answer when we get it. So we substitute in the numbers. Equals frequency times by 20. To get frequency by itself, we divide both sides by 20. And our answer for F is 15 million hertz. Remember, you need to work it out in kilohertz, therefore we need to divide by 1,000. We divide by 1,000, we just get rid of the last 3 zeros there, and our final answer is 15,000 kilohertz. Okay, continuing on. Electromagnetic waves form a continuous spectrum from a different wavelengths. What is the proximate range? This unfortunately is something that you just need to learn. You just need to know, and the answer is this top box here. You just need to know that gamma rays, as you know, have the shortest wavelength to radio waves, which have the longest wavelength, radio waves. There. Next question. Infrared and microwaves are used in communication, as we've seen before. Give one example of infrared waves used in communication. Now, there are 3 things you need to know that infrared waves are used for. Electrical heaters, cooking food, including infrared cameras. But the one that you need to know in terms of communication are for remote controls. You do not get the mark if you write, for example, mobile phones, or you can say for data transmission as well. I would always suggest, however, to go for the remote controls because they're really easy to remember that one. Some scientists think there's a possible link between mobile phones and male fertility. So fertility is in males the ability to reproduce, to produce offsprings, or in this case human babies. Here are their study. What's interesting, it seems that the numbers decrease. So the sperm count decreases if you spend more time using mobile phones per day. So there's a negative correlation. The more hours the mobile phone is used, the lower the sperm count. However, these results do not necessarily mean that mobile phone causes reduced sperm count. You are suggesting, so not necessarily knowing the answer, one reasons why. Very simply, it could just be other factors involved. Other factors, such as age, for example, such as if someone smokes, or someone's diet is different. It can be any of these factors. Okay, question 5. Microwaves are electromagnetic wave. Which one has a lower frequency to microwaves? Now, if you remember, if I did my diagram before, the one with the lowest frequency, remember L is always going to be towards the radio waves, and after microwaves it will be radio waves there. Okay, what do all electromagnetic waves transfer from one place to another? Well, they transfer energy. What's good reminder is that EM waves do not transfer matter. That is really key that you know that they transfer energy, however they do not transfer matter. Okay, next question. Picture shows a tennis coach using a speed gun and seeing how a player serves the ball. We have a frequency here of 24 and lots of zeros there, hertz. Now if you work it out, this should be 2.4 times 10 to the power of 10 hertz. and we know speed, 3 times 10 to the power of 8 meters per second. You're calculating the wavelength of a microwave, and in this case, let me just add it in as well, frequency, and also this is V for speed. So here is my equation added in already, and so we put our numbers in. So the frequency is 2.4 times 10 to the power of 10 hertz. This one is 3 times 10 to the power of 8 meters per second. And we're calculating the wavelength, and it hasn't asked us to change any of the units, so there we'll keep it in standard unit of measurement, which is meters. Finish it into our equation here. 3 times 10 to the power of 8 equals 2.4 times 10 to the power of 10 times by the wavelength. We are going to divide both sides. 0.4 times 10 to the power of 10, and our final answer, if you do your calculation of on my sheet, .0125, and remembering we need to have our units meters, so 0.0125 meters. Some of the radio waves, microwaves transmitted by speed gun are absorbed by the ball, and what effect will that have? Well, the ball will become hotter. It's like when you put food in the microwave, the water molecules will absorb the microwaves and therefore causing the food to become hotter. Okay, one final question left. It says here, different wavelengths of light can be used to transmit information along optical fibers. Now, I've underlined optical fibers because you need to know what they are. They are glass or plastic fibers that carry data as pulses of visible light. Actually, what happens, I've drawn a picture here. Light is reflected, and this is how data is transferred from one place to another. So the graph below shows the percentage of incident light transmitted through the fiber, and that varies, that changes by the wavelength of light and the length of fibers. So there are quite a few things that we need to understand in this graph. There are two lines, one with a shorter fiber length and one with a longer fiber length. We also have the wavelength, and then we also have the percentage of incident light transmitted. So the question is, you are comparing the percentage of incident light transmitted from the two different types of fiber over the different wavelengths. So the first thing I notice with both of them, so both of the lengths, so I'm looking at both of them now, it seems that as wavelength is increasing, they are both decreasing and then increasing. Both of them have this kind of dip. So that's what I'm going to start off with. So as both for both the fiber lengths, as wavelength increases, going from 4 to 6.5, as that increases, the percentage of incident light transfers seem to decrease, and it seems about 5. At 5 times 10 to the power of negative 7 meters, they start to increase again. And what you can say specifically is at 5 times 10 to the power of negative 7 meters. We should add the minimum transmission. So for both of them, where they have the minimum light transmitted is at 5 times 10 to the power of negative 7 meters. But the maximum transmission, the highest, I would say, if we look across, is about 6.5 times 10 to the negative 7 meters. And it's either or, you can add that for that second mark. Lastly, looking at the fiber length, which one has a greater, oh, the lights are turned off. So this last question, it says here, which one transmits a greater percentage of light? Well, the one which is higher up is this dashed line here, and it is the shorter length fiber, and that is the 50 meter fiber, so the shorter length fiber. And there we go.